Good morning. This is the 29th lecture of the lecture series X-ray crystallography and solid state chemistry. We will be talking about the structure of some organic compounds as per syllabus of this X-ray crystallography and solid state chemistry. Okay. This would be the last lecture of this lecture series, which hopefully will complete the content of the syllabus for X-ray crystallography and solid state chemistry of a public university of Bangladesh. Well, we have been talking about solid structure of materials like ionic compounds, covalent compounds, metals, non-metals, alloys, and different many classes of compounds, but not the organic compounds, the structure of organic compounds. But syllabus says that we have to describe the structure of flavones, isoflavones, and alkaloids. So naturally, one can say why only these three? Because there are so many different classes of crystalline organic compounds. Why only these three? Well, one thing may be correct, that if we take all the organic compounds of the known compounds, then this syllabus would not be completed by 30 lectures or 28 to 30 lectures, which needs for 2 credits courses. Okay. Anyway, for this reason, we are taking some natural products of organic compounds, flavones, isoflavones, and alkaloids. Okay. So what we do when it says flavones and isoflavones, we have to take the structure or describe the structure of flavones and isoflavones. Then we can definitely say which type of compounds these flavones are. What are flavones? What are flavonoids, I say? Well, we see that flavonoids is a class of compounds which has got main subclasses, and out of these 6 main subclasses, flavones and isoflavones are there. So if we talk a little bit about flavonoids and see their key aspects of flavonoids, and then we take specific flavones and isoflavone structure, I would say that that would be the main idea of talking about the structure of flavones and isoflavones. What are flavonoids then? Flavonoids are a diverse group of natural polyphenolic compounds. Where do we find it? We find it in plants. And that compounds responsible for vibrant pigments in fruits, vegetables, and flowers. The compounds are antioxidants, anti-inflammatory, antiviral, anti-carcinogenous properties, providing cardiovascular and neurological health benefits. So you see, flavonoids are very important class of compounds. Key aspects of flavonoids: where do we get flavonoids? It is found in fruits, vegetables, tea, red wine, herbs, and nuts. Role in plant. Flavonoids role in plant. Flavonoids defend plants against UV radiation, pests, and diseases. Health benefits. Flavonoids help fight oxidative stress, reduce chronic inflammation, protect against neurodegenerative and cardiovascular diseases. So what we have to discuss only flavones and isoflavones, these two compounds. flavones and isoflavones out of 6 subclasses of flavonoids. Okay, then we talk about flavone. This is a class of flavonoids, as I said, and if we get the molecular formula of flavones, that is C15H10O2, and you can see that here are 3 rings, one C6 rings, another C6 rings, and a C3 ring. So that rings naturally referred as A, C, and B rings respectively, which is given in figure. You can see that the flavonoids has got 3 functional groups. What are these 3 functional groups? Hydroxy, carbonyl, and conjugated double bond. So it gives typical reaction of all 3 functional groups. Flavonoids are colorless to yellow crystalline substance which are soluble in water and ethanol. The yellow color solution when dissolved in alkali flavonoids are moderate to strong oxygen bases and are soluble in acid. And if we see that you can see that pK value is about 0.8 to 2.45. Flavor has planar structure, so it has got a COC bond about 120.9 degree. Its bond length at C oxygen bond length is 1.376 angstrom, and its dihedral angle is about 179.2 degree. Flavonoid molecules are often stabilized by hydrogen bonding, and it has got pi stacking reactions. We will see when we do the crystal structure, we see that these flavonoids crystallizes in low symmetry system. What do we mean by low symmetry system? Low symmetry system means that it could be triclinic space group, or could be monoclinic space group, or maximum could be orthorhombic space group. Okay, so these are the 3 space group flavonoids could be crystallizes. Okay, now this is the skeleton structure of flavonoids. Look, this is the C6 ring, and this is a C6 ring, and then a C3 ring is attached here. And similarly, isoflavones, here is the skeleton structure of isoflavones, like diazine, and here we see that this is again C6 ring, and the C3 ring. Okay, this slide shows us there are many derivatives of flavones and isoflavones. I just take 2 of derivatives of flavones and 2 derivatives of isoflavones and give their structural properties. Here, if F1 is a derivative of flavones, and it crystallizes in space group P21 by C, and its cell parameters are given below, and here you see that if it is P2 by C, then that means that it's a monoclinic system, and the cell parameters A, B, C, and beta, and it has got 4 formula unit in the unit cell. Okay, the molecular formula we have shown it in the earlier slides, so we will get 4 formula unit in the unit cell with having these cell parameters. Okay, another derivatives of flavones are 4-trifluoromethyl-7-methoxyflavone derivative, whose space group is P bar 1. What does it mean? That means this is a triclinic crystal system, And cell parameters here are the all six cell parameters, and the formula unit in the unit cell are 2. Okay. Similarly, if we go for the isoflavones, two common isoflavones, one is genistein, and another is diazine. The space group for genistein is P2O1 by C, which has got the same space group of F1 derivative of isoflavones, but the cell parameters are different, and that is this one is monoclinic. This genistein is monoclinic system, and cell parameters are as follows. And diazine is also having a space group 2,1 by N. You remember this N glide and this is C glide. That's the reference. Okay, and the cell parameters is given below, saying that and the formula unit for this one is 4. This is how we can describe the crystal structures of flavones and isoflavones. We'll go to the next structure. Now we are talking about alkaloids. In broad sense, alkaloids are naturally occurring organic compounds that must have at least one nitrogen atom in the ring, usually in the ring. These properties often have a bitter taste and can trigger strong physiological and psychoactive effects in human and animals. So, why does alkaloid exist in nature, plant, fungi synthesis? Alkaloids primarily defense mechanism because they are often bitter and toxic. Alkaloids help repel insect herbivores and competing microorganisms, allowing the organism to survive. Do we consume alkaloids? Oh, yeah, of course we consume alkaloids almost everyday life. Caffeine is alkaloid. We found it in tea, coffee, chocolate, etc., which gives us nerve stimulation. Nicotine, found in tobacco. Morphine and codeine, found in opium poppy. Powerful painkiller. Quinine is historically used to treat malaria. Atropine, found in belladonna or deadly nightshades. Here you can see the molecular skeleton structure of five alkaloids: morphine, quinine, epinephrine, styrosine, and nicotine. Okay, we go to the next slide and see a little bit more. We take common 3 alkaloids and see how we can see the structure of these 3 common alkaloids. Caffeine. It's a natural stimulant. Where do you find it? Coffee and tea, as I said. Its 3-dimensional shape has 2 flag rings joined together. It forms monoclinic crystals. That means this caffeine is crystal system is monoclinic. And how do they stack? How we see 3-dimensional structure of this caffeine? The flat molecules stack on top of each other like a deck of cards, and this shows also a force called pi-pi interaction. That means this has also got hydrogen bonding. Morphine, what it is? A strong painkiller, as I said, as we mentioned, and the 3D shape. Morphine is not flat. It has a complex shape made of several band rings, and it includes methyl groups and an amine that reaches out to the connect to receptors. How they stack? The band rings lock together in a tight 3D net, and this hold together by hydrogen bond as like magnetic snaps between the oxygen and nitrogen atoms. What is quinine? as we said, it was a drug for malaria, and the 3D shape of quinine is made of two main parts. One, a flat quinoline ring, and then a complex cage-like quinolidine ring. How do they stack? The 3D crystal form spiral shape, helix shapes, and the monoclinic molecules linked together through their nitrogen and oxygen atoms to form a 3D double helix shape. We take this one. This is a structure of morphine. Here the structure of morphine, and it seems a little bit complicated, but do remember, when we know the space group, unit cell parameter, there are lots of software which can draw the structure of the compound for us using that. So morphine is molecular formula C17H19NO3, and this crystallized in the form of space group, and P21, 21, 21, that means it's an orthorhombic system. Unit cell dimension A, B, C is given there, and unit volume also. Molecular illustration, it says that it is a T-shaped core of molecule. Or crystal packing motifs, molecular geometry, the structure consists of 5 fused rings forming a highly considerable molecular architecture. 5 fused rings, 1, 2, 3, 4, 5 fused rings. And okay, and then the pyridine ring adopts a slightly distorted chair conformation. If we talk about 3D structure of the anhydrous quinine, and its molecular formula, you see, as it is C20H24N2O2. Do remember when we are talking about alkaloids, we say alkaloids, but must have a nitrogen in the compound. So here, if we go to the space group of this anhydrous quinine, P21, and that is a monoclinic crystal system, and as I said, its intermolecular forces, hydrogen bonding network. Unit cell parameter, if we go for the high resolution X-ray diffraction data, shows that its unit cell parameters or precise cell parameters are A, B, C, beta, and volume is this. So these values are here for the structure of the anhydrous quinine. What are the highlights of the structure? The asymmetric unit of the structure, the 3 crystallographically independent molecules. That means Z is 3 here. Double helix motif. These independent molecules packed together by a strong hydrogen bonding, wrapping into a unique pseudo 3 two-fold axis and double helix supramolecular chain. Confrontational flexibility, the overall packing architect is heavily influenced by the steric placement of flexible benzyl group in the C3 position and methoxy group in the quinoline core. That what is the structure of anhydrous quinoline. Okay, this what we have been talking, and isoflavones and alkaloids. Here in these slides I have given at least 4 reference where in details we can get flavones and isoflavones and the structure of alkaloids. So this can be a consultant to get more information about these compounds, and there are also references in this paper from where you get, if you are interested, deep information and structure information about these 3 compounds. Okay, then we come to the end almost, that this course had a syllabus, had 7 sections. The sections was, first section was solid. We had to have differentiate between different solids, then crystal lattice and crystal systems, and then elementary crystal optics. We accept diffraction by crystals, and then order diffraction techniques and single crystal data collections, and it is a reduction of data. All these have been discussed very extensively discussed. And then this last section was structure of solids, and we have discussed close packing and interstitial sites and different types of compounds and their structures. And also the last section was structure of some organic solids, that is flavons and isoflavons and alkaloids. That is all about this lecture series, which I said that it is meant for undergrad student, and generally in the last year of the undergrad it has been taught. And the syllabus content I took from a public university of Bangladesh, and I hope those who just were with me could understand a little bit of X-ray crystallography and structure of solids, and hopefully I could create some interest, and thereby you will, if you are interested, you can go through other textbooks and enrich your knowledge on structure of solids and X-ray crystallography. Thank you so much for being with me. We hope that this will at least give you some basic idea about X-ray technique and structure of solids. Thank you once again.